And let's just dive into some of the foundational components of cloud computing and recap them. And it's a very timely topic in the world that we live in, and I think this is a good place to start. So if we go to cloud computing, what's the point? That might be one of the best places to start with cloud computing. You know, why would anyone do cloud computing? Can't you just use your laptop for everything? And maybe that's the why. And if we can't answer this, then this is a good reason to not use cloud computing. But I think we can answer this question, and probably the best place to start with this is this concept of infinity or near infinity. And the key problem with your laptop, physical data center, any of these types of single-use technologies, like only I can use my laptop or only my company can use the data center, it's stuck with some things that cloud computing addresses, problems that cloud computing addresses. And one of them is the elasticity. And that's a core capability that ties in with this infinity concept, is that I can scale up and grab more resources, or I can also scale down and have less resources. And this concept of on-demand or elastic computing, we see this as well with many technologies that we're taking for granted. A good example would be getting food delivered to your house, right? That's an on-demand capability. You're not constantly getting food delivered to your house. You just ask for it and then you get it, and then you could ask for another order of food and they could keep bringing food delivered to your house. It's very similar in when you're building computer systems. You don't always want to have this huge cluster of machines. You want to right size it so that just for the demand that you have at that moment, you can use the correct amount of CPU and disk. So this is one core problem that really you cannot address with traditional computing. Another one that it addresses is the concept of high availability. So high availability, what that means, high availability, we'll just call it high avail. High availability means that also is weakly tied to this concept of infinity. And what that means is that you have a service that it's available when you make a request. So you have a customer here and it makes a request to a service, and it always gets a response back. And this is very difficult to do well with a traditional data center, because you only have the traditional data center. You would have to do some kind of other architecture in order to get a highly available cloud computing infrastructure. And you would have to get another backup data center or multiple data centers, put them around the world. But with cloud computing, because there's this unlimited pool or almost unlimited pool of servers, you can make sure that your service has another capability built into it that supports highly available. And let's get into that. So that would be redundancy, and so or fault tolerance. Redundancy or fault tolerance is related to highly available in that it's a building block. So in the case of this highly available service, why is it highly available? Well, it's highly available because you can get more capacity, and additionally, you have more than one set up. So you have a load balancer in front, and the load balancer, even if one machine goes offline, it can listen to the health check metric and the health check metric will tell it which server to send a request to. So in this case, because you're able to ask for as many redundant layers of machines that you need in order to fit your requirements, you can have a highly available service. So again, it goes back to this concept of elasticity. So this is just the start of some of the problems that cloud computing solves. But I think these concepts are so important that it's important to start with this and to get into how critical it is to make sure that you're doing these characteristics when you're building an application. In the old days of the internet, when companies were first building things, they weren't taking into account these facts, and that's why many companies had outages. And even companies today will have outages and have issues because they're not following these rules. So these are almost like the rules of modern computing, is that almost like a checklist, right? You go through your checklist and you say, is my capability elastic? If it's not, then you need to fix it. And then another checklist would be, is my system highly available? If it's not, you need to fix it. Is my company fault tolerant, or does it have a layer of redundancy? And oftentimes, unfortunately, even today, even for people using cloud computing, they are not fully taking advantage of these characteristics. And if you're not, then that's a problem. So let's get into a few other things. So this is maybe the foundations of cloud computing, but let's get into the really some of the other things that are opened up with cloud computing. So another one that is an interesting one is data science. So let's just talk about data science in cloud computing. The last one that we talked about was more just the foundations that were refer to anything in the cloud, data science and cloud. And this is a very interesting topic because, again, many universities especially are not actually doing cloud computing. Even at the elite level, there's some, but it's a very small amount. Maybe it's, let's just say it's right now at the academic level, I would say it's anywhere between 1 to 20% of universities are even approaching some kind of cloud capacity in their curriculum. So what's happening is that there's now this disconnect between the university system. Here's a university system. And then also the real world. I think it's getting fixed, and that's a lot of the stuff that I teach. But this is a issue, is that the university system right now, at least in data science, the majority of companies are focused on research that is not cloud computing related, and the research is non-cloud. And likewise, in the real world, the most of the companies that are deploying applications are on the cloud. So we've got a problem. and in particular, we've got a problem with data science because there's a whole set of problems that don't work with traditional data centers. So let's talk about this. In particular, one of the problems is this data lake problem. And the data lake is an interesting concept that it sounds simpler than it really is. But what a data lake does is it allows, again, back to our other slide, it allows infinite disk storage, infinite disk I/O. So really from a computational perspective, it opens up a bunch of solutions that really don't exist in a laptop environment. So disk I/O, it opens up storage. We have effectively infinite storage. We also have effectively infinite network, because this is a highly available network, and also it's software-defined storage as well. So this is all dynamic, and it's this cluster of storage that has these capabilities that you don't get from a laptop. And also the data lakes, like let's say Amazon's data lakes, have actually 11 nines reliability, which I think is somewhere between like a millisecond per year or a couple milliseconds per year, something very low downtime. So effectively, it's not possible for this to be down. There's too many layers of redundancy. So what this does is allows a data science practitioner to solve problems that really were not solvable before. And one of the ways that you would use a data lake would be to do ML ops. So what this means is that you can now go through and provision, training jobs. You can also go through and version your ML models. You can also go through and provision GPUs. There's all these capabilities because you don't have to move the data, right? So this is a key component of a data lake, is the movement of data. It goes away. When you have to move the data from your laptop to some other location, or from your data center to some other location, the time involved is non-trivial, and that could potentially stop all work, because you have to figure out how to transport your data all over the place. But if instead you build inside of this data lake and all of your raw assets live inside, and the computational components like the managed machine learning system can communicate with the data lake, then you're able to fully take advantage of cloud computing. So this is what I've experienced right now, 2020, still. Again, as I mentioned before, most even elite universities have not even approached this cloud computing for data science. Now, I think it's happening. It's going to start happening very quick for many reasons, but there's a huge advantage for students or for people in industry to take advantage of being an expert in data science and cloud computing, because there are very few true experts. Even though it's been around for a long time in the world of data science, there's a lot of, I would call it like toy-based data science. And the toy-based data science is basically it only works on my laptop. And how can we tell if it's a toy data science? Well, that's one. Another one is the tool chain, right? So now there are some fun problems you can solve without being in the cloud, but one of the issues to consider is, does your library, like your data management library, does it even work? So on bigger data. And if you take, for example, a really popular library in Python called pandas, that's got a critical thought process baked into it. And one of the critical thought process that baked into it is that you're going to be using small data. And why is that baked in? Well, it requires 10x the RAM to actually solve a problem. So let's dig into what problem that creates. So if you have a laptop that's very powerful, like you have a laptop that's, let's say, 32 gigs of RAM, or something like that, which is pretty powerful laptop, but you're dealing with a data set that's let's say not that big, but let's say it's 4 gigabytes of data, right? You've now potentially are going to require 40 gigs of RAM just to work with that data set, and now that's a relatively toy data set, and you can't even process it on your laptop. And so it's not even an option. And the only possible way to deal with it would be to do a trick. So you could go through and you could, and I've done this before, you could truncate your data, and you could sample your data. You could do some kind of trick, or you just abandon that tool altogether, which is, again, one of the most popular tools in toy data science, and go right to the cloud and then build a cloud-based machine learning exploration where you use the cloud-based tools. And so then at that point, if you do this enough, then you may ask yourself, why am I playing with toys? Why don't I just use a real tool? Why don't I use a tool that solves all my problems so that I don't have to go back and forth between? So this I think is one of the more interesting problems that 2020 we're having, and that I do believe is going to get solved this in the next year or two, is that majority of top universities will have no choice but to quickly adopt cloud computing and start to do data science where they take advantage of these capabilities. So that gets me into the next topic, which is cloud native. And this is another fun topic, and cloud native is an interesting word, and what this means is that the system has been designed designed for the new capabilities. A lot of times what happens in software, and it's not a bad thing, so a lot of times in software you want to be efficient, and so you just bolt something on that you did before because it's easy, but with cloud native, you're designing systems that use these capabilities that the cloud offers that didn't exist before. And we know that one of the capabilities is the infinite capacity, right? Infinite CPU, infinite CPU storage, things like that, network. And so that's a good question when you're thinking through how to solve a problem. Is the problem cloud native? So if we go back to that other example and we talk about pandas, is pandas cloud native? No. Pandas is designed to be a tool that has limited power, right? It's designed to be work on your laptop. So pandas, even though it's the most popular data management library in Python, it's not a cloud native tool. Now there's more than likely going to be some cloud native tools that will be able to work on your laptop, and they'll be able to work in the cloud. And so that's a good, maybe litmus test for, is my tool cloud native? Another example that would be web frameworks. This used to be a big thing in maybe the early days of 2000 and beyond, where someone would build some kind of web framework that would talk to a relational database, and then that relational database would be the source of truth, and then you would grab some HTML and kind of render out this page. Now that's also not a cloud native technology. So we can even put this in here, like maybe we can put a section that says non-cloud native, non-cloud technology. So a good examples of that would be pandas, the most popular framework in Python. We can also say web frameworks. Web frameworks in general are systems that carry baggage from the 1970s. So this is really people that may not even be alive anymore were building some of this technology, and even the internet didn't exist, where a lot of the baggage of these still live. So internet, the you know, so a question that there's no right answer, but a question when you're using these tools is, why am I using something that really was designed for a world where there wasn't an internet and there wasn't a cloud? And I think that's a very important question when you're deciding to build something is, do I need to use a tool that carries all that baggage? And another concept of non-cloud would be monolithic, right? That's another non-cloud native way of thinking. And what monolithic means is that it's this giant application where every single thing lives in it and it does everything. And another non-cloud, we call this like maybe we could call this non-hints. These are hints that you're dealing with a non-cloud technology. Another one is heavy relational database. And again, there's nothing wrong with a relational database, but if every single solution is you're using it because that's what we always did, that's often also a hint. Now let's look at the cloud native. We know it's designed for new capacities. It has some of these infinite capabilities with it. It's also got those core traits that we talked about. You know, it's got the elasticity built into it, high availability, HA. You know, these are cloud native techniques. And also another one is microservices. So this is a good hint that you're dealing with a cloud native technique, is that a microservice is the one way to define it is it's a function that maps to a web service. So it could be as small as this one little function and it maps to a route. And we'll just say this, like it looks like a route. And these are capabilities that the cloud has enabled, and partially it's enabled this through things like serverless technology. And serverless is a big word, but in general, it encompasses things like a AWS Lambda. It also covers things like Google Cloud Functions. It also covers things like containers. And this serverless technology allows you to do things like microservices, and the function gets mapped to some compute component of the cloud. Some other cloud native technologies as well in serverless would be the data management layers. So we talked about the non-cloud native ones like pandas, but they're cloud native ones. There are things like, for example, Athena with AWS, and what Athena does is lets you do a on-demand SQL-based query, on-demand SQL query to your data lake, and so this is abstracting all this complexity and turning the SQL language into something that doesn't talk to a relational database. It talks to your cloud database. Likewise, there's also Google BigQuery is another example of this. And this is really a key component of all this, is that you're able to use these tools that are not designed in a limited environment. They're designed for an infinite environment. And I think this is really important for many people to think about when you're building technology, is where did it come from? So what was the factory that your technology was built in? If the factory was built in was people that were designing the technology were designing it in an era where there was no internet and there was only physical data centers, or even some of these technologies were designed without the concept of even a data center. They're just designed to work with a physical server. That these capabilities are going to be very limiting. But if you're looking at evaluating a technology stack and you're building it for the new world, so 2020, no matter how much buzz or hype or evangelism that people have, or people build software foundations for these technologies and they're hyping them up. Well, why are they hyping these up? People like to stay the same, right? That's something that you'll often find in academics. You also find this in the software industry, is that people want to just keep everything the same. Don't change, because then they have to learn something new. Well, unfortunately, you have to always learn something new with the IT industry. Every 6 months, I think it's a good metric. What is different? What has changed? How do I learn something new? And this happens to be what the new thing is cloud computing. And one of the ways that you can evaluate the technology is that it meets these specs, right? Designed for new capabilities, has some infinite capabilities. You're looking at microservices. You're looking at serverless technology. And this also gets into some, we'll just call this cloud native part 1. Let's get into cloud native part 2. In part 2 of cloud native, the other thing that's a big part of cloud native technologies is DevOps. And we'll build this cloud native and DevOps. So why is this a big deal? Well, DevOps, let's just define what DevOps is first. It's a term that gets thrown around a lot, but what DevOps is a combination of several different components. One is that it is a cultural shift. And let's go ahead and build this. So we'll see a cultural shift here. It's also the culmination of automation. So that's a big component of DevOps, is that you're able to automate the environment that you're in. Another component of it that manifests in this is that you're building, and I guess it's a subcomponent of the automation, is you're using things like continuous integration and continuous delivery, and we'll define those in a second here. Let's say continuous integration means that you can test your code every time you check it in. So test on check-in. And then on continuous delivery, it means you deploy, or your code is always in a deployable state when you check it in. And likewise, with DevOps, you often are using microservices. And why microservices? Well, because they're small and they're designed to use cloud components, right? So in a way, DevOps, even though I think it hasn't been called out as much as it could, the DevOps environment in a way is cloud native. So you really can't fully adopt DevOps without the cloud. And so if you're saying you're doing DevOps and you're not using the cloud, you're not using DevOps. And the other component of this is probably the speed and agility. And we can dive into each one of these components here. So the automation is somewhat straightforward in that you are testing your code every time you check it into GitHub. Your code is also deployable. automatically, but each of these components, why are they able to be, why does this automation exist, and how is it made possible with the cloud? Well, one of them is that infrastructure as code couldn't exist in a physical data center environment. It doesn't even make sense. And why does it not make sense in its current form is that in the cloud, you have software-defined ecosystem. So I can define software-defined compute. I can do software-defined storage, software-defined networking. If I can't programmatically create my infrastructure, I can't fully use infrastructure as code. And infrastructure as code gives me the ability to do this full automatic deployment. Likewise, if I have some web framework that somebody built that they're hyping up right now that was really designed in early 2000, uses a relational database from 1970, that's when the relational database was built, you're not using microservices, you're using something that someone designed before the internet existed. Instead, if you're using something that's a serverless technology, or using cloud functions or something small, then you can make these little teeny changes, and then you're giving yourself the speed and agility. And this speed and agility also comes into play with the project management. And so project management has to be designed in a way that allows you to do these kind of deliveries. So I think what we could do is this is from a high level the DevOps components, and why this topic is such a big deal is that you're able to deliver. I mean, I guess maybe that's a good way to define this, is like, why would I use DevOps? Is that I can make here, we'll put this as a why here, is that I can make changes many times per week or many times per day. So that's one of the reasons to use DevOps, is that changes happen many times a week, many a week. So this is also almost like a test, is how many times are you deploying your code per week? If it's once, probably not using DevOps. If it's 10, maybe you're doing DevOps, right? Like just or can you do 10 deployments a day to production? Then you might be doing DevOps. Another concept as well are you using cloud? You can you're fully adopting the cloud technologies. That's another reason to use DevOps, cloud native technologies. Another reason is that you're able to build products faster that create product speed. You're able to make revenue, more revenue, or higher quality products because you have this great feedback loop. So I think I can go into each one of these step by step and then describe why they're so important to DevOps. So let me go into culture first, which is an interesting one. So culture and DevOps. This culture here is an interesting one, and we can start with the word Kaizen. And Kaizen means continuous improvement. So here we go. And this is a critical component of getting DevOps right. Is it is a feedback loop where I say, is it getting better? Like so basically, everything, is it getting better? Is the deploys, are they getting better? What about the quality of my code? Is it getting better? And this is a Japanese word. It literally, Kaizen means continuous improvement, and it comes from the the post-World War II world, post-World War II world where people were in Japan were working with American statisticians and building the automobile industry, and in fact, Toyota was the big benefactor of this, and they came up with things like Six Sigma, and it has a lot of relationship with this continuous improvement concept. And the continuous improvement concept with Six Sigma, why does it matter? Well, what is Six Sigma? Let's talk about that. That Six Sigma refers to the fact that if you look at a normal distribution, we have the median here, and inside of the median, within 3 standard deviations away, right? This is the first standard deviation. This is the second, and this is a third, and likewise, this would be the negative standard deviation, the negative second standard deviation, and then negative third standard deviation. You have something like 99% of all events occur within 3 standard deviations to the left or to the right of the median, right? So this is just the nature of a normal distribution or a bell-shaped distribution, and in particular, so this is bell, normal, and in particular, what's interesting about this is that you can now use that as a way to fix things, right? So if something pops up over here, or it pops up over here, like you're building a bolt, and the bolt is either too big and it's over 3 standard deviations too large, or it's undersized by 3 standard deviations from the median, then you know there's a problem somewhere. And the problem is actually shouldn't be something that occurs frequently. It should be extremely rare, and you can fix it. But if it pops up, if it starts popping up, you know that something needs to get fixed. And that's really the feedback loop is, okay, we found a problem, it's outside our range here, it's not in our Six Sigma, let's fix it. Let's get to the root cause. And how do we do this? Well, we use something called the 5 whys. And the 5 whys will get us to the root cause. And the 5 whys is a interrogation technique that works with Kaizen. So let's say, I think a better example would be to look at a software system that a company built. A lot of my career has been working with software systems, and so one of the ways to start with this would be this would be the first question is we're having defects, and part of the defects might be because we're doing work that we don't need to do. So the first question would be, why are we writing software where we duplicate the same code all the time, right? This is a classic sign of a problem. And then somebody in my company says, well, the tools are broken. All of our tools in our company are broken. And then the next question would be, well, why are the tools broken? This doesn't seem like a good idea. And then they would answer, well, because we are too busy to fix the tools because we have hard deadlines, and the managers don't want us to fix or the managers want us to hit these deadlines. So now we're getting a little closer here. So the management team wants things done on time, but they're telling you to do things that are inefficient. So you're in a circle, like you're working 4 times harder than you need to be, and you've never fixed the root problem. So then the next question would be, why don't we just fix the problem? Why don't we just fix the tools? That way we can be more efficient. And then the answer would be, didn't think about that. Maybe we should fix the tools. And then the 5th question would be, why don't we approach management? Why don't we talk to the management and tell them, listen, the reason why we're always behind is we're doing 4 times more work than we need to, because all of our tools are broken and we're cutting and pasting the code everywhere, and that's why we're always behind. If we fix the code, fix the tools, then we only have to write the code once, and we could be 4 times better, right? And so that would be an example of, we could improve, right? We could get better immediately by getting to the root cause, and then also not accepting the failure, right? And so this is a cultural component that drives into this concept of continuous improvement. So this works very well with cloud computing because you have all these capabilities that you can feed into this continuous improvement concept. So, but it is very important to focus on this, and this is probably still a problem at many organizations, is that it's easy to not make continuous improvement because the default state is to be average, and this technique will make you above average, right? This is in fact a process that will destroy mediocrity, right? Kaizen is a way to actually make sure that you're not average. Okay, so that's culture. Now let's get into the deployment, the difference between continuous integration and continuous delivery. These are often confused. So continuous integration which is called CD or CI, sorry. And then we have continuous delivery. And they sound the same, but they're not. And it's easy to confuse them. So let's define both of those terms, CD. So what is continuous integration? It means that my source control, which let's say it's GitHub, I'm checking in my code and I put it into GitHub, and then what happens is there's a build server, and the build server will automatically go through and check my code. So it will run maybe a test. It will also maybe lint the code, and so what this is it's a continuous integration process. So it means that every time I check in the code, this is a check-in event. So we'll call this check-in. There's a subsequent build step, and the build step will lint my code and test my code, right? And so this is the feedback loop here, is that I'm always able to make sure that my code is in a testable state. And so the reason why this is so important is that it's really actually it goes back to Kaizen, right? I'm continuously improving. So this is the cultural tie back, but it's also common sense that, why would you clean your kitchen? Well, you don't want to get sick because there's raw meat on the counter, right? Or why would you, drink clean water, right? Because you don't want to get sick because your water's clean. Same thing. Why would you put code that has problems into your system? You only want things that are high quality, and so this ensures that you have quality. So the continuous integration component, there's zero excuse for any software project, even toy projects with the technologies we have now, to not use some form of continuous integration. If you're not using continuous integration, really you're not doing professional software development. There's no excuse to not have something, just like some kind of process that's constantly checking your code. I would call it negligence to not have this. Now the next step is continuous delivery. And with continuous delivery, what happens is that you take this to the next step. So let's let's go here and let's again draw GitHub. And with GitHub, you are also checking in your code. Here we go. We check in this code here. And then again, the build server goes through, and the build server will do the same thing. It'll test the code, maybe lint it, but it does another thing too. If this passes here, if the code passes, then what happens is that it will deploy the code to an environment. And this is also where the cloud comes in, is that typically this deploy step is actually possible because the source code itself contains the infrastructure. And this would be the infrastructure as code piece. And it allows dynamic creation or change of the infrastructure. So you can spin up new environments, like a development environment, a staging environment, a testing environment, a production environment, and dynamically tweak that on every deploy. So what's happening is the cloud environment is set up, right? So this could make sure that the cloud ecosystem set up, and in addition, your code itself is put into that cloud environment. So it lays it out, plus it puts the code inside, and it also goes through and it tests it and lints it. And this is why these are two different topics, is that the first topic, it's been around for a long time, continuous integration. It just means that I have a build server and it goes through and it tests my code and everything works fine. But in continuous delivery, not only are you linting, testing, but your code is designing the infrastructure, and the infrastructure is built and the code gets deployed inside of there. So what this allows is that you can, in fact, be constantly testing your infrastructure, testing your cloud environment, testing your code because it's actually deployed into the environment. And this is also a truth serum for someone doing DevOps. If you're not doing this, you're not doing DevOps. You're doing something else. You're probably using an older methodology that's less effective. So these two steps, though, are often very confusing to people because they hear CI/CD and they think it's the same thing, but they're related in that the first step is testing, but they're different in that the delivery means it's literally deployed and the environments themselves are dynamically created. Now let's talk about these build servers, right? They sound magical. Let's get into what are the kinds of build servers that you'll find. So this is another interesting concept in that it also ties back into the cloud. So what are the kind of build servers that are available? Well, one of them that's available is a SaaS build server. And so a SaaS build server is interesting because it often has a YAML configuration with it. And so this is a plain text configuration file. A good example of this would be GitHub Actions. GitHub Actions allows you to build things out and automatically test them. Another example of this would be Circle CI, would be another example of a SaaS build server. There's also cloud native build servers, which have some relationship with SaaS, and they may have some of these similar things here. But one of the interesting things about the cloud native build servers is that they're often coming from the cloud vendor themselves. So a good example would be AWS has code pipeline. And why do they have code pipeline? Because it deeply integrates into their cloud environment and makes it easy to work with their cloud system. Likewise, Google Cloud has, I think it's called Cloud Build. GCP has Cloud Build, same thing. it integrates deeply with, let's say, Google App Engine or other parts of their cloud ecosystem. And then likewise, Azure has Azure Pipeline. And so that's also there we go, Azure Pipeline. So that's also a cloud native technology. And so why would you use these things? The core reason for these is they have deep integration to a cloud environment. So the advantage of these is that there's less hoops to jump through if you're doing, let's say, a serverless deploy, or you're building something in the cloud and you want to do continuous delivery, right? We just talked about how powerful that is. Well, you may have the best experience for continuous delivery by using the cloud native deployment tool. There's a third one and we could call this maybe like proprietary or open. I guess we'll just call this third-party build servers. And so the third-party build servers, a good example that's probably the most popular one would be Jenkins. And why would someone use something like Jenkins? That it has some disadvantages over the cloud native build server in that you don't get the deep integration. That's one disadvantage of it. But the advantage of it would be that potentially you have more power because you can configure Jenkins to work with any operating system. So Jenkins, for example, will work with AWS. It will work with GCP. It'll work with Azure. You can install Linux on it. You can install Windows on it. You can install OS 10 on it. You can deploy mobile apps. So it's a lot more flexible because it's just a Java file or a WAR file that the Java interpreter, when it's running, will make a build server with. So if you need more power and flexibility, then that's why people will use Jenkins to deploy something. But in general, this is one of the choices that a company that wants to adopt DevOps will need to make. And again, it ties back in again to cloud native, right? Is that more than likely, if you're fully embracing a cloud native environment, you'll probably use a cloud native build server so that you can fully adopt the cloud and use all the capabilities that are necessary. So let's go to the next part of the cloud DevOps lifecycle here, which is project management, which seems really boring to many people, and I agree it's not a fun topic necessarily, but it's important. And if we talk about Agile and project management, one of the things that Agile in theory is supposed to do is have something called a sprint. And so in this sprint, what you do is you are protecting a unit of work. So we know that microservices, for example, are a small function that gets routed to a web service. So let's say that we're building a microservice here. Here we go. Here's a microservice like this, and we have a function here, and it maps to a route. We'll just call this API or something like that. And in theory, this is pretty small, and it could map really well to like a 1-week sprint. And if you dig into this, how would you design this so that you can constantly be building new services every week? Well, one thing to do is to break up what this 1 week means. How would you make the structure for this in a company? Well, one thing to consider is that there's 5 days per week, right? So we have 5 days, and in that 5 days, what are the real times that a developer could even work? My experience as a manager, and I've managed many projects, is that you have 4-hour blocks. So here we go. You have a 4-hour block here, and you have another 4-hour block here, like this. My experience is that you have each day 2 4-hour blocks. So, and those are units of work that you can task something to, 2 4-hour blocks. So in theory, you only have per week, in the most perfect scenario, 10 different tasks that you could accomplish. So this fits really well with a microservice, is that in fact the microservice, like you could even break it up into pieces, like maybe you say, like, task 1, which is a block, would be write the code, write the function, just write the function, right? And you could estimate this, and you could say, okay, that's 4 hours, great. And then you could do the next one, which is maybe integrate the API. So, integrates API. So that's another 4 hours, right? And so now you're already down 1 day. So 1 day is gone, right? And then you could maybe do, like, build the infrastructure as code for it. That's another 4 hours. Anyway, you can just keep going down the list here, and basically, like, a microservice and a 1 week sprint fit pretty well. But if you're not using Agile, you're going to have a problem every week delivering things. And this gets into a very important question at most organizations, and that is, what are you building each week? And it's a very important question. And it's probably not what people think they're building. So many times a software company says that they're building software, or they're building cloud computing, or they're building something, but what's coming out of the factory, just like a car manufacturer, we know we have 10 different blocks, 10 blocks each week. So in theory, you could do 10 different tasks that are intellectual tasks, but each week, if you're not producing something like a microservice and deploying it into production, then what are you producing? What are you doing? And a lot of times what's happening is you're producing meetings, and your company is dragging someone in, and they're, like, going back and forth and talking to the boss, and so you're actually producing each week meetings. And do those meetings actually provide value to your customers, or to your company? Can you make money going to meetings? The answer is no, you cannot do that. So that might be something to think about. Another one is tickets. This is the classic problem that happens a lot, is that someone will create a bunch of tickets in a ticketing system, and inside the tickets, it'll be we're going to do this, we're going to do this, and then it's an explosion of tickets. And it turns out that still, what did you produce that week? Nothing came out of the factory. There's no microservice. So your company's building tickets. So you're building meetings, you're building tickets. Another thing that could happen is you could be having outages, and so your company is building outage response. So your company is building responses to the outages. So this is just a way of thinking of either you're producing something each week, or you're I guess a better way of putting this is you're always producing something per week. In the Agile project management sense, it should be an improvement to your company, a microservice, a new change. But oftentimes, people are doing ineffective project management, and what they're really producing is meetings, tickets, responding to outages. And so this does now tie back again to culture. And let's talk about how this could affect how this actually comes out to play. And part of it is, this is what I would call is fake Agile. So fake Agile is a real problem. And fake Agile is just like fake news, right? When somebody doesn't understand, this is actually a big problem in the media. Is even a lot of politicians actually don't understand the difference between linear, log, and exponential, and it's very clear that they don't understand this. And that we know the difference here is that when you have something that goes up, that's exponential. When you have something that has a logarithmic, that's like a human, right? A human is logarithmic. That's log, that's exponent, and then linear is something that has an equal relationship between x and y. Similarly, with fake Agile, it's a lot like fake news, where people say, oh, they don't know what this means, so they assume that things are linear, which is what happened in the U.S. with a lot of the politicians. They ignored COVID-19. But same with fake Agile is you're saying you're doing Agile, but what's really happening each week is you have a ticket system, and the ticket system is just got tickets all over it. And then it turns out that all you do each week is move tickets, and you move tickets. And if the management in your company looks at those tickets and they say, oh, look at this is great. Look, we're getting all this work done. But it's just like the fake news, where you're just putting fake information out that means nothing. The real truth is a demo. And so a demo is greater than a ticket. A ticket is just saying something. It could be helpful if you do it right, just like the news can be helpful if it contains facts. But a demo is the truth, right? So if you demo the microservice each Monday, and you say, look, I just built a new microservice, that's not fake. That the microservice has been built, you demonstrated that it worked. But if what you demo each week is a ticket, that's fiction. This is like saying, oh yeah, don't worry about it. We got it under control. We stopped COVID-19. Don't worry, it's all good. And then a month later, oh no, we stopped COVID-19. It's good. It's good. Don't worry about it. And then meanwhile, in the U.S., what happened was we had politicians who were fake news. They would say, hey, we got it. We're don't worry. Oh, it turns out they actually couldn't solve this, right? Because they were dealing in fake news and creating fake things. Same with fake Agile, is if you say fake things all the time, eventually what'll happen is that's what you produce, is you produce the fiction. And so that's why I think COVID is a really good example. When you see people make things up, then what happens is you get a bad outcome. Likewise, if you go to the truth and you truthfully show every week, you demo and you do a weekly demo, you know that's the thing you built, and you can't fake it, right? I have an application, it works. Let's build the next service. There we go, it works. And so let me show how does a company get into fake Agile, which I've seen a lot. One of the reasons why people get into fake Agile is similar to some of the problems that we've seen with COVID, is that it's really an authority issue a lot of times. And the airline industry, there's some good examples of this, where the hippo would come in and cause problems. And let me explain what a hippo is. The hippo we know is like I don't know if I can draw a hippo. Let's see, I might be able to. We'll see a big old hippo here. And what is a hippo? A hippo is the highest paid person's opinion. And the hippo is not always right. right? So we know that again from the U.S. The president of the United States, I think, is a really good example of even if you like him, he's very confident and often wrong, right? So a hippo, that's the core characteristic of a hippo, is confident and wrong, and this doesn't fit well with Agile. Is what's better than this is to be humble and to admit that you don't know anything, and that's how you build successful software. Is instead of the highest paid person in your company coming in, going to developer, tapping them on the shoulder, hey, we need to change this feature. Instead, you say, look, I don't know how to fix everything. Let's build a process where it's not constantly randomizing what we're doing each day, where chaos is our process. And I think that's a big thing that happens at software companies. Is every day you're randomizing developers, and you're telling them to work on something else every day. And so this goes again back to the factory of what you're doing every week. If the most powerful person in the company is going to each person, telling them to work on something constantly, then you basically have a chaos-driven environment. And those 10 4-hour blocks, what's happening is that they're gone. They just got wiped out, because every time someone starts to get ready for work, the highest paid person comes in and says, hey, no, actually, let's come over here. Let's work on this. And eventually what happens is nothing ever gets produced. Instead, what you're producing is fake stuff, right? And so this, as I mentioned before, you see this in the airline industry as well. They did a lot of research into why a crash occurred. And let's just show a picture of the airplane here. And one of the things that they found out with the airline industry is that in different cultures, they have more respect for authority. And in some cultures, the crew member would go to the pilot and say, hey, I think we're out of the fuel. So the fuel is gone. And then the pilot, who is more powerful, the hippo, would say, hey, I don't want to hear that. That's negative. I don't want to hear that information. That's not what I'm concentrating on. I'm trying to get us to where we're going. And then they would tap again and say, hey, listen, yeah, I think we're going to die. I think we're going to die. There's no more fuel left. Hey, I don't want to hear that. That's negative. I'm in charge. Quit talking to me. And then we go, and then boom, the crash, the plane goes down. Eventually that happened enough times. They say, hey, maybe the boss is not always right. We should listen to everybody. We should build out a process where every person's opinion, we should at least consider what they're saying. And that's one of the ways that they've addressed problems in the airline industry. And I think both in terms of the software industry and also politics, you see these same issues addressed. And this again goes into the DevOps culture. It sounds like it's not has to do with the DevOps culture, but it really does. Let's go back again now to this, and let's tie it all together. So if we look at this DevOps topics that we just talked about, right? We have culture here. We have automation. We also have project management. So we'll just call project management. And then we also have the microservices, and these are just similar. There's other things too, but these are all kind of part of this feedback loop of Kaizen, right? Which is that either you're getting really it's a 3 different states. So what are the states? The states are, am I getting better today? Am I the same? Or am I worse? And there's no better example of this than something like COVID-19, right? Where you can see ineffective management is you're either better, you're the same, or you're worse. There's no there are no other states. When you're trying to fix something that's a dynamic system, these are the states you're in, and this is what DevOps does: is you're constantly looking for ways to improve. You're measuring yourself, and you're using the culture to make sure that you respect everybody's opinion, build a good infrastructure. You're building these small services like these microservices, and then you're also using automation, and the automation will make sure things happen automatically, and then you're effectively using project management, and the project management is designed so that you can protect the workers in your company, and that you are truthfully addressing what's getting built each week, not pretending you're building things each week. You're specifically demoing each of these things. So again, the DevOps mindset and cloud computing are very tied together, and in fact, it's hard to separate the two things, because some of these components are only available in a cloud-based environment. In theory, you could do some of this without the cloud, but it's this feedback loop that the cloud has enabled. So that's, I guess, one of the things to really consider with cloud computing. If we kind of wrap this up, is okay. Now what is the cloud? And it really, I think the summary is that it's a way to practice Kaizen, right? Which is continuous improvement. It's also a way to speed up delivery, right? We know that the cloud can speed things up. It can make things more reliable. And also, we know that the cloud has new capabilities. It has advanced capabilities that didn't exist before. And those capabilities, we call them cloud native. And also, you could even say that it's the building block for AI, right? So if you don't have cloud computing, you really cannot build AI solutions, because of the fact that you need this infinity sign, right? You can't build AI. The AI capabilities require GPUs, it requires high storage, high compute, elastic infrastructure, APIs that do natural language processing. This is really the foundations of AI come from cloud computing. So and part of this as well is it requires a new culture, right? And the culture, the new culture has to be different than the culture that we see that's a dysfunctional culture. So it's very easy to see dysfunctional culture, and we pointed out some of those things. Is the hippo runs it, so the hippo has to go away. They have to hunt the hippo. The fake things have to go away. You can't be producing fake news, fake tickets, right? You need to have a culture that is designed to continuously improve things, and to have teamwork, so that you're doing things where you all have a unified mission. You're trying to build things that have high standards of excellence. And so there's a huge cultural component of cloud computing, and also it's something that implicitly supports DevOps. So that's my summary of cloud computing, and I think that's a good place to maybe wrap it up. Okay, so any questions about those topics?